is equal to mu2, which claims the population means from two separate populations are equal, right? And then alternative hypothesis can claim mu is not equal to mu2. Well, these cases will be two-tailed tests, right? Or you can say, if you want to find out more exactly whether it's less than or greater than, okay? Then, of course, the corresponding null hypothesis will be a greater than or equal to mu2, or mu1 is less than or equal to mu2, okay? So depending on the context of the problem, you can run one-tailed test or two-tailed test, just like before, okay? And many times you will see this format of null and alternative hypothesis. So instead of saying this, you can actually say mu1 minus mu2 is equal to 0. So this claim and this claim are identical, saying the same thing, right? Or you can say mu1 minus mu2 is not equal to 0. Okay? And the textbook prefers this way, okay? Because it has some benefit when you're dealing with trying to find out whether it's upper tail test or lower tail test. We need to find out whether it's greater than 0 or less than 0, right? So for example, this is the same. Another way to write this claim is mu1 minus mu2 is what? Greater than or equal to 0 versus mu1 minus mu2 is less than 0. So from this alternative hypothesis, you can find out we're running what? Upper tail test or lower tail test? Lower tail test, because it says less than 0, right? So you have to set up the rejection region on the lower tail, right? And so on, okay? So that's the only difference between one sample test and two sample tests, okay? So going back to the first slide, okay? In this chapter, we're going to talk about a few different concepts. First of all, testing equality of population means assuming that those two populations are independent. So you are selecting samples from two separate populations, right? That's the first case. The second case, you are comparing population means related sample, which means you are selecting two samples from either one population or related population, right? So you might wonder, why would you do that? I mean, if you are trying to find out whether the two means are equal or different, right? Why would you select the two samples from one population? Okay? Well, you will see that. You will see why, because just to give you an idea, in reality, in practice, many times we run pre-post test. Okay, pre-post test means simply before and after. We're comparing before and after. Sounds like some TV commercial for cosmetic surgery. Before and after, right? Is there any difference between before and after, right? But in business setting, suppose you are a production manager, right? And you changed or improved some production process, right? So you want to find out whether there's any difference between, let's say, in the defective ratio, right? Before the new process and after the new process, right? So does the process make any difference, right? So that's the idea. That's the case of the second here, right? Population means related sample, okay? Population proportions, well, we always talk about the proportion after the means, right? And then the population variance, okay? All right. So first thing we're going to deal with in this chapter is we're talking about the testing the difference between two means, assuming they are from independent samples, okay? And even in this case, we have to separate two different cases, right? The first one is sigma 1 and sigma 2 are unknown, but they are assumed equal. Okay? So when you select, when you have two populations here, and selected the sample here, right? And we have population mean 1, population mean 2, sigma 1, sigma 2, right? Two, well, standard deviation or variance, it doesn't matter, right? They're the same thing, right? So can we assume that two populations have equal variance or not? Okay? Depending on that question, right, we have to use two different types of testing, right? So first case we're going to deal with is, reasonably, if you can assume that sigma 1 and sigma 2 are equal, in other words, two populations have equal variance, right? Then we're going to use what we call pooled variance test, pooled variance t-test, okay? But if you know that sigma 1 and sigma 2 can be different, or you cannot assume that they are equal, if you have sufficient evidence for this, or if you have a reasonable suspicion that they could be different, right, then you have to use different tests. It's called the separate variance t-test or Satterthwaite t-test. Okay? So we're going to talk about two different cases. So here our underlying assumptions are, first of all, two samples are selected from separate or unrelated sources, unrelated population. Okay? And another assumption we have to have, because we are running t-test, okay? You have to either assume that the populations are normally distributed, or, you can have the sample size at least 30, right? Because then you can apply CLT, central limit theorem, okay? Okay? All right. I'm sorry, what?
Why is the assumption include both of
Instead of or?
Instead of and or.
Why? I mean, if you know the populations are normal, then you don't need large sample size, right? But if you don't know what the populations are normal, then you need the large sample size. Okay? Okay. Yeah. Okay. All right. So we talked about this. This would be the lower tail test, one tail test case. This would be upper tail. Again, it depends on this sign on the alternative hypothesis, right? Or you can run the two-tail test. The difference would be half of alpha here and entire alpha on each tail, right? Exactly same thing as before, right? Well, the only difference here is, in case you can assume the two populations have the same variance, right? Equal variance, then we can calculate the pooled variance between the two populations, right? And the way you do it is using the sample standard deviation or sample variance from the first sample and second sample variance from the second sample. Using the degrees of freedom like this, we can calculate the pooled variance. This is called the pooled variance, right? And then, using that pooled variance, we can calculate the standard error for this t statistic, right? So the same, it looks pretty similar to our old regular test statistic, t statistic, right? But here now we're dealing with the difference between the two sample means, difference between the two population means. Remember, these are hypothesized means, okay? So you can either say, typically we run these cases, right? Mu1 and mu2 are equal, right? This claims mu1 and mu2 are equal, and mu1 and mu2 are not equal, right? But sometimes if you have some reason, right? Let's say you have two different processes, right? And from the first process, the size of measurement should be, say, 4 inches, right? So you have very reason to believe that mu1 should be 4 inches and mu2 should be 2 inches, right? And you want to test, you can test that mu1 minus mu2 is 2 instead of 0, right? You can even run that kind of test, right? Do we have any sufficient evidence that the difference between the two population means is equal to 2 versus not equal to 2? In other words, you don't have to use 0 all the time. You can use any number you like, right? Depending on the context of the problem, right? So in that case, this mu1 minus mu2 would be 2 instead of 0, right? Okay? Just like, we ran the previous example in the one sample example, we used what? T is, what was it? 42 minus 50, right? Whatever, right? So what that means is in this case, null hypothesis claim that mu is 50 versus not 50, right? But our sample mean came out to be 42, right? So that was a sample mean minus mu, right? Some hypothesized number, right? So the same idea. It doesn't have to be 0 all the time, right? Although typically, because we are comparing whether two means are equal or not, right? So in most cases, we'll be using 0 for this number, right? Okay, so that's the structure of the test statistic. So the only complication in this case is you have to do some calculation, right? And calculate the pooled variance. Once the pooled variance is calculated, then the rest, okay? Here, using this test statistic, in order to calculate, find the critical value, you have to know the degrees of freedom. Degrees of freedom for this T statistic is n1 plus n2 minus 2. Just remember that, right? It's logical, because when you had one sample, it was n minus 1, right? When you have two samples, basically the double of that, right? So it's n1 plus n2 minus 2. Okay. Yeah, so that was the case of hypothesis testing or point estimate. Using the same idea, same standard error, you can think about the interval estimate, right? So the difference between the two means, the two population mean, right? You can be certain percentage confident that the actual difference between the two population mean can exist within this interval, right? You can do that, right, if you like. So let me just give you this example, and I'll let you go, right? So is there a difference between the dividend yield between stocks listed on the NYSE and NASDAQ, right? Dividend yield is a financial concept, right? But dividend is everybody understands Korean here, right? So it's a 주식 배당, right? Dividend yield, right? The share of profits distributed by the company, right? You divide that by the price of the stock. That's the dividend yield, right? Anyway, so here we have 21 stocks from NYSE, 25 stocks from NASDAQ, right? And sample mean came out to be, and standard deviation came out to be like this, right? So can we claim that the average population dividend yield are equal or different, right? So you can do that test, right, at 0.05 level, right? So the null hypothesis claims that mu1 minus mu2 is equal to 0, or this, right? Or is not equal, or this. So we're running two-tailed test, right? So when you calculate the pooled variance using those numbers, comes out to be 1.5021, right? So test statistic comes out to be 2.04, right? And using the degrees of freedom of 44, right, we find out the critical value is 2.0154, right? But our test statistic is 2.04, so that's slightly larger than 2.015, right? So our conclusion is reject the null hypothesis, and we have sufficient evidence that the two population means are different, right? Or the average dividend yield is different between NYSE and NASDAQ, right? So that's the first case. We covered the first case, which is the unrelated sample or two independent population, and we assume the equal variance, right? Okay. Any question? All right, so this is the last chapter, chapter 10. Make sure you read the chapter thoroughly before you come to Tuesday's class. Have a good weekend. Have a good holiday. I'll see you on Tuesday. So we started talking about two sample tests last class, and I gave you there are a few different cases, the independent samples, related samples, and among the independent sample tests, you can have either the equal variance, unequal variance, okay? So we just talked about the first case, the independent sample assuming equal variance, and the name of the test was pooled variance t-test, okay? So the test itself is exactly the same as before, null and alternative hypothesis and so on. The only difference is we have to calculate this pooled variance, okay? And using the pooled variance, we obtain the standard error for the t-test statistic, okay? And once you calculate the test statistic, and you go ahead and use the same procedure and make the conclusion, okay? There's nothing difficult. And you could also calculate this standard, using the standard error, you could calculate the confidence interval, okay, for the difference between the two population means, okay? Okay, before we talk about the unequal variance example, let me show you how to run this t-test using Excel, okay? So if you go, I think this is the question number 10.12, the problem number 10.12 in both editions, okay? So why don't you open and read this problem to understand what the question is about. $10.12, okay? And if you read the problem, you see they're talking about two different banks, Bank 1 and Bank 2, okay? And these are their waiting times before you see the teller or someone who can help you, how many minutes, I believe, right? You need to wait, right? So the question is there any difference between waiting time between Bank 1 and Bank 2, okay? So we're talking about, you can run either two-tailed test or one-tailed test. Null hypothesis, mu1 is not equal, is equal to mu2. Alternative hypothesis, mu1 is not equal to mu2. Or you can write it this, mu1 minus mu2 is equal to 0. Mu1 minus mu2 is not equal to 0. It's up to you, okay? All right? Or if you want, you can run the one-tailed test, okay? So we have the data here, the 15 observations from each sample, okay? And the way you run the t-test is here. You go to data analysis, and among the choices, you will have 3 t-tests, okay? t-test 쌍체 비교. This is a paired difference test. This is the last topic we're going to talk about today. Okay? The second one, t-test equal variance, assuming equal variance. Okay? And the last one, t-test here, is a different or unequal variance. Okay? So let's try the first one first. Okay? So I think if you read the problem instructs you to assume equal variance. Okay? All right, so if you click on here, all you need to do is specify the two data a range. Okay? And I would include the label. Okay? And then highlight the other data. And since we have included the label, make sure you check the label here. And you can specify here what do you think the assumed difference is. Okay? So if your null hypothesis goes like this, then you would just say 0 here. Right? But as I mentioned last class, if you want, you can test whether it is 2 or 2,000, or if you have any reason to suspect that the population mean difference between the two populations is any number, you can do that, right? But typically in our case, we would specify 0 here, okay? And you can change the significance level of significance, okay, if you want, okay? But let's try 0.05 here, okay? All right, and then I already have the output here, but let me show you what happens if you do it on the other different area. Okay, so yeah, as soon as you click that, you get this result. Okay, so we have two sample means from first sample and second sample, variance of two different samples, number of observations are 15. You don't have to have equal number of observations when you're running the t-tests for equal variance or unequal variance. When you have paired difference tests, you have to have equal number of observations. I'll tell you about it later. Okay? All right. And then here, pooled variance right here. It already calculated pooled variance. Okay? And so based on that, it gives you the test statistic here. Okay? Test statistic comes out to be negative 4.13, right? So we have test statistic T is negative 4.13, okay? And then the decision rule, you can write down, reject the null hypothesis if the test statistic is less than T of alpha divided by 2 degrees of freedom, or greater than T of alpha divided by 2 degrees of freedom, okay? Make sure you specify the decision rule here. Well, Excel doesn't know whether you're running one-tailed test or two-tailed test. Okay? So kindly it gives you both cases, right? So the p-value for one-tailed test is 0.000146. So in case you run so we have the t distribution here. And our test statistic came out to be negative 4.13. Okay? So if you're running one-tailed test, okay, that p-value is 0.0001. Right, basically, right? And then if you're running two-tailed test, you have to multiply, add this area to the other area. Is 4.13, right? That's going to be another 0.0001, okay? So if you're running two-tailed test, p-value will be twice as large, okay? 0.00029 something, right? So, you can use the p-value and you make the decision immediately, right? What is the decision or conclusion? By looking at the p-value. Reject the null hypothesis because p is less than alpha, right? You are using 0.05 as alpha level, and p-value is, if you're running one-tailed test, it's 0.0001. If you're running two-tailed test, it's 0.0002 or 3. right? So you can easily reject the null hypothesis, right? Okay? That's how you run the t-test on Excel, right? Any question about how to use Excel to run t-test? At least equal variance, assuming, right? All right, we'll come back to this example later. All right, so what if you cannot assume the equal variance, or either you don't know or you have some reason to suspect that the two populations have different variance, okay? So, you know, examples can be, if you're dealing with completely different population, right? Let's say you're comparing number of customers numbers visiting banks versus restaurants. So you have collected some data and say number of customers, and say we have bank and restaurants, and let's say Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay? So you have collected data, right? Then, you know, we have completely different characteristics between bank and restaurant. Of course, restaurant people go to enjoy, right? So maybe over the weekend, right? And they may have more customers visiting, right? But in the bank, I mean, you probably go to bank to conduct some business, your personal finance or whatever, right? So, you know, you cannot assume that in two different populations you will have equal variance, okay? Then maybe you have to assume unequal variance, or at least you have to test, okay? So in case you decide that the two populations have unequal variance, right? Then you have to use special test called the separate variance t-test or Satterthwaite test. Satterthwaite is a name of a statistician who introduced this special test. Okay? The test itself is a little bit different, and our textbook doesn't deal with it exactly, right? So I'll just let you use Excel, okay, in your homework and other projects, okay, when you're running the test, when you need to run the test in reality. You can just go to Excel and choose data analysis and unequal, assuming unequal variance between two populations. Okay? And then the way you use it exactly the same, right? Okay? So we'll run this test a little bit later. Okay? But more importantly, I want to talk about how to decide whether you should run the equal variance test or unequal variance test, or pooled variance test versus Satterthwaite test. Okay? Well, that's our next topic here. So, if the difference between the variance between the two populations is very small, right? Then there will be virtually no difference between the pooled variance test and the Satterthwaite test. Whether you run this test or that test, you will get pretty similar result, okay? If, in fact, the variance between the two populations the difference is pretty small, right? Well, so in order to find out, we need to run the F-test. F-test is used to test to see whether two variances are equal or different. Okay? So the null hypothesis goes like this. Right? Null hypothesis says two variances are equal, alternative says two variances are different. Okay? Or you can, this is a two-tailed test, or you can run one-tailed test. Okay? And obviously, as you see here, this is an upper-tailed test. Okay? In F-test, F is sigma 1 square over sigma 2 square, right? The comparison of two variances, okay? And as you see, F statistic cannot be negative because we're talking about something squared divided by something squared, right? Variance over variance, okay? So F's, the shape of F's distribution goes like this. Okay. And the minimum value it can take is 0, okay? And maximum it can take, of course, infinity. Okay? What else? And the F statistic has 2 degrees of freedom. Lambda 1 and lambda 2, 2 degrees of freedom. Okay? So first degree of freedom is for the numerator. The second degree of freedom is for the denominator. So depending on the number of observations in 2 different samples. Okay? Of course, if you have same number of observations between the 2 samples like this, then the degrees of freedom will be the same. Right? In this case, it would be 14, 14, n minus 1 over n minus 1. Okay? Okay. So before I forget, let me mention this. If you go to data analysis, and if you look at the choice, there is F-test. Okay? However, this F-test is different from what we use in here, right? So do not use this function in Excel, right, for our purpose. Okay? Because what we are doing here, we either talk about two-tailed test or only upper-tailed test. Actually, most likely we will be talking about upper-tailed test here, because if you see here, when you construct the test statistic F, S1 square over S2 square, we always put the larger sample variance on top as the numerator, right? So, for example, if you look at this printout, right? Excel calculates 2 variance from the first sample, variance from the second sample, right? So you would always put 4.33 on top and use it as a numerator, and 2.68 as denominator, right? That's how I calculated F statistic here, right? So test, if you're running F test, right, in order to find out whether you should run equal variance test or unequal variance test, right? You have to calculate the test statistic, and that is F6 divided by E6. So this one divided by this, because this one came out to be larger. Okay. All right, and then for critical F value, you can use the table. If you go back to at the end of your textbook, there are F tables. Okay. But let me show you this table. Okay. F table. Well, this is the same F table, but I just took it for just alpha level of 0.05, right? So F table has the same structure. This one has the same structure as the F table in the back of your chapter, back of your textbook, right? So on top here, the first row, we have degrees of freedom 1, okay? And this W is supposed to be backslash, okay? But somehow it shows as W, shows up as W, all right? And that means this first column is degrees of freedom for 2. So this one is degrees of freedom for numerator. This one is these numbers are degrees of freedom for denominator, right? So, for example, we have 14 degrees of freedom, 14 degrees of freedom. So our critical value should be 2.48, something like that, right? All right, let's see what we got. Right. Critical F value, what did I do? I used 15, okay. Let me change it to 14. So either you can use the table if you don't have the table available, or if you have computer available for Excel, then you can use this formula. F inverse, right? That gives you the critical value for F statistic, right? And specify alpha and degrees of freedom 1 and degrees of freedom 2. And then, yeah, you will get 2.48, right? Okay, so you can either use the table like this. Where is the table? Okay. And did I close the F table? Oh, okay, here we go. 2 Excel, okay. All right, so make sure you understand how to use the F table to find the critical value. You'll probably see the same table in your final exam, okay? And again, if you want to use different alpha level, you have to use a different table. There's a separate table for different alpha level, okay? Okay, so, you know, the test, running the test will be exactly the same as before, okay? We have the null and alternative hypothesis. This is the test statistic. And remember, degrees of freedom are n-1 and n-1, okay? Okay, so if you're running one-tail test, you would set aside an entire, if you're running one-tail test like this, right? You will set aside entire alpha as the rejection region and find the critical value. If you're running two-tail test, the only difference is you will divide the alpha level by 2. So instead of using 0.05, you would use 0.025, and you have to find the critical value, which means you have to use entirely different table, okay? Okay, so let's say we are running one-tail test. Suppose, because, you know, we put the larger sample variance on top, right? We are running this one-tail test, okay? And then based on that, you can make a conclusion, okay? And the decision rule is right here. Reject the null hypothesis if the test statistic is greater than F, okay? Critical value, and so on, okay? And let's use an example here. Suppose we have two different markets here. And the question here is there a difference in the variance